All right, guys, today I want to talk to you about a problem that we're faced with in science, and it has to do with renewable energy. Basically, there's a limited supply of fossil fuels or carbon-based fuel, and we will run out eventually. So before we run out, the whole world is trying to scramble and figure out what type of renewable energy can we use to replace fossil fuels. And so I've listed a couple of scenarios here. The first scenario was solar energy. Awesome source of energy, but it only works during the daylight hours, and so that's not good. What will we do for electricity in the evening? Wind, same thing. It's an excellent source of energy, but it only works when the wind is blowing. You know, sometimes the wind doesn't blow as strong. And then the third thing to consider would be electric cars. When we run out of gasoline, we're going to have to figure out how to make these cars move. The issue with electric cars is that the batteries often die after a short period of time and are expensive to replace. And so in all three scenarios, we need some sort of storage like batteries, but there's some issues with batteries, as you'll see in a minute. Dr. Brennicke from the Department of Chemical and Biomolecular Engineering at the University of Notre Dame is currently working on ionic liquids and how they might be used to make safer lithium-ion batteries. As you may have seen in the news recently, the hoverboards with the cheap batteries, they kind of burst into flames on laptops and things of that nature. That's based on a design flaw in the lithium-ion battery. The way a battery works is on the cathode side, which can be some sort of aluminum base, has a connection to the anode side, which is some sort of copper base. But basically, an electrolyte, which is like a saltwater solution, or, well, it's a solution that involves some sort of salt. Lithium is actually is like a salt, and so the lithium ions have a positive charge, and so they can carry an electron across from the cathode side to the anode side. And so when we charge a battery, really that's what takes place, is that the electrons kind of piggyback on the lithium ions, and the lithium ions travel through the solution and carry them over to the other side. Then when we disconnect the battery from the charger, if we take a wire and connect it to the anode side and then move it all the way over to the other side on the cathode side, then the electrons have a path to flow back to where they came from. And that's electrical storage. The problem with this is that the lithium electrolyte solution combo, it causes dendrite growth, and it's corrosive at times. Sometimes we don't use water, sometimes we use some sort of acid or something like that. And it'll grow or crystallize across, and that shorts out the battery. And so organic solvent is also flammable in some cases, and that's why those hoverboards burst into flames. So their possible solution would be an ionic liquid, and an ionic liquid is just a pure salt that is liquid around room temperature, and they're just simple salts, you know, and they're non-flammable. They act just like an electrolyte because they're conductive. They have high stability at a high temperature, and they're chemically diverse. You can make literally hundreds and hundreds of ionic liquids. And so another way to combat the dendrite growth is that you can make a membrane separator to block the dendrite growth, but you want to make uniform holes that are just big enough for the lithium ions to pass through. So in theory, the lithium ions can pass through the holes, but the dendrite growth cannot. One of the issues that we run into, though, is that when we take these polymer membranes and we soak them in an ionic solution, there's some swelling that occurs. So we need to use some sort of science and mathematical modeling to predict how big the diameter of the holes will be once we soak them in a specific ionic liquid. And so what we're asked to do is two things. One is we need to figure out, how do researchers at the University of Notre Dame use science to approach this problem? And then secondly, how can high school students such as yourselves play a role or play a part in this battery design process?